So, exchanging energy between system and surroundings. So, we've talked about the exchange of heat energy. It's the mass times the specific heat capacity times the change in temperature. And we just talked about the exchange of work, pressure, volume, work. So that's minus the pressure times the change in volume. And so the heat can go either way between system and surroundings. The work can go either way between system and surroundings. And you can actually have the work going one way and the heat going the other way in the same process. Or they can both be going in the same direction. So there's lots of possibilities here. We do something called calorimetry, and this name suggests metry, measuring calories. So this is studying and measuring the amount of energy. Constant volume energy, constant volume calorimetry is where the volume is not going to change. So the change in energy is equal to the Q, the heat, plus the work. And we can do that by measuring heat and work, but that can be challenging. So it's easier if we arrange things so that the volume doesn't change. If the volume doesn't change, remember W? We're simplifying this a little bit, believe it or not. We just talked about this pressure volume work where there's a pressure and a change in volume. If the change in volume is 0, then the work is 0. If the work is 0, then the change in energy is just equal to Q. Much easier to deal with. So at constant volume, the change in energy for a reaction is just Q. And we put a little subscript V there to mean the heat at constant volume. And doing an experiment at constant volume, even with gases, is not too terribly difficult because you put it in a sealed container and you just don't let the volume change. Put it in a rigid container of a fixed volume and then the volume doesn't change. Then all you have to deal with is the Q. And the Q is easier because we can measure that with the change in the temperature. So it isn't practical to measure temperature changes of the individual chemicals, like the block of copper and the water together. What we do is we measure the change in temperature of the surroundings, and we use what's called a bomb calorimeter. This is an insulated, controlled system. It's got a fixed volume. We don't have to worry about things leaving the calorimeter. And so the system, which is inside the calorimeter, the heat of the system is equal to negative the heat of the surroundings. The heat of the surroundings is negative the heat of the calorimeter. So we've got the calorimeter and we've got what's inside of it. And so we measure the heat of reaction by observing the change in the temperature of the surroundings. We know the temperature of that piece of metal because it came to the same temperature of the water. We can measure that. It's hard to measure the temperature of a piece of metal. If you've got multiple chemicals all together, it's hard to measure the temperatures of them individually. Here's an illustration of a bomb calorimeter. It doesn't actually look much like a bomb. But here's one that's used for combustion reactions. So here inside, we have the sample, and we've got oxygen in there, and we have some wires coming in so that we can ignite this substance. And it burns inside of here, and we can measure the heat that's given off to the surroundings here. This water inside this outside container is part of the calorimeter. This substance and the oxygen in here is the reaction. This is the system, and the surroundings then are the bomb calorimeter. We have a thermometer in here. We can measure the temperature change of the water and tell how much heat was given off by this reaction. So we have a calorimeter constant, which is the heat capacity of the calorimeter, which is the amount of heat absorbed by the calorimeter for each change, each degree rise in temperature. So Q is the heat capacity of the calorimeter times the change in temperature. The calorimeter is not changing in mass. The calorimeter has a particular mass, and so it has a particular heat capacity. This is not the specific heat capacity, this is just the heat capacity. So we can measure delta T, we know what this is, so then we can figure out what Qcal is. Qcal is the opposite of Q reaction. The heat given off by the reaction is equal to the heat gained by the calorimeter. I don't feel like that was a real great explanation, but anybody have any questions? Yeah, there'll be more later. Okay, so let's do this example. When 1.550 grams of liquid hexane undergoes combustion in a bomb calorimeter, the temperature rises from 25.87 degrees to 38.13 degrees Celsius. Find the change in energy for the reaction in kilojoules per mole of hexane. The heat capacity of the bomb calorimeter, which was determined in a separate experiment, is 5.73 kilojoules per degree Celsius. Okay, so I'm going to draw you a picture. You can see I am not an artist. So here we have the reaction occurring. Here's our hexane, and it's burning. And here's the calorimeter. And the heat capacity for the calorimeter is known to be 5.73 kilojoules per degree Celsius. And that calorimeter had a change in temperature. I'm not doing anything with equations yet. I'm just picking these numbers out of here and figuring out what they mean. Thinking about what happened. So inside, we had hexane and it burned. When things burn, it gives off energy, right? Where did the energy go? It went into the calorimeter. The calorimeter got warmer. So the energy given off by this reaction is absorbed by the calorimeter. What happened? It went from 25.87 to 38.13 degrees Celsius. So we can calculate the change in temperature for the calorimeter. The final is 38.13. The initial is 25.87. .13 minus 25.87, 12.26 degrees Celsius. We're given a mass of the hexane, so maybe let's put that in there, 1.550 grams of that. Now, have we done something with all of the numbers? Yeah, we have, right? Here's the mass down here. Here's the heat capacity of the calorimeter, and we used the final and initial temperature of the calorimeter to find the change in temperature. So now we need to think about how can we find out what we're looking for? Well, we want delta E for the reaction. So this reaction, we want delta E for the reaction. Change in energy is heat plus work. Is there any work going on here? Is there any change in volume? No. This is constant volume. So then delta E equals Q. Right? If W is 0 and delta E equals Q plus W, then delta E must equal Q. Well, we'll call that Q for the reaction. The reaction generated energy and gave it to what? The calorimeter, right? So the heat lost by the reaction equals the heat gained by the calorimeter, right? Because the heat of the reaction plus the heat of the calorimeter has to equal 0. First law of thermodynamics, the energy of the universe is not changing. Whatever was lost by the system has to be gained by the surroundings. Again, I'm running out of space, so I'll do this. The heat lost by the reaction is equal in magnitude but opposite in sign to the heat gained by the calorimeter. Could we figure out how much energy was gained by the calorimeter? Let's look at what we know about the calorimeter. We have this number that's kilojoules per degree Celsius, and here we have a temperature change in degrees Celsius. What unit do we get if we multiply those? Kilojoules. Is kilojoule a unit of energy? Yes, it is. So Qcal, there's that negative, so I have to keep the negative. Qcal is that 5.73 kilojoules per degree Celsius times the change in temperature, 12.26 degrees Celsius. The units helped us know what to do.
So we didn't need the mass.
We don't need the mass. We don't need the mass of the calorimeter because this is a heat capacity. It's not specific heat capacity. Specific heat capacity has a gram unit in the bottom. It's kilojoules per gram degree Celsius or joules per gram degree Celsius. And we use that for substances. This calorimeter is not going to be changing in mass, and this C is particular for this specific calorimeter. Each calorimeter is going to have its own specific, its own heat capacity. So, yeah, that's a little potentially confusing. So we don't need the mass of the calorimeter. Well, this does tell us something. This tells us that this calorimeter, for every degree change in temperature, must have an energy change of this many kilojoules. So as long as we know the temperature change, we can calculate the amount of energy that it absorbed. So that is that 5.73 5.73 times 12.26. That should have 3 sig figs, 70.2498. And that's going to have a minus sign on the front of it because of this minus sign. And the units on that, which I didn't have room for, are going to be kilojoules. That tells us that the that Qcal minus Qcal was minus 70 kilojoules. Q reaction equals this, right?
So the reaction gave off the heat.
Mm-hmm.
Okay.
So Q reaction equals negative Q cal, which we just calculated, minus 70.2498 kilojoules. But what does that question ask us for? It wants kilojoules per mole of hexane. This is all very nice, this number right here. That's why we need the mass of the hexane. It is possible that they would just throw numbers in there, though, just to mess with you.
That's why I was confused why we didn't.
Yeah. So this is how much energy was released by this mass of hexane. Okay, that's not a real useful number. You can't really go use that for something else. It's not all that useful. It's much more useful if we know how many kilojoules for every mole of hexane. Can we figure out how many moles of hexane this is? Sure we can. We're going to need the molar mass of hexane, and the mass, I'll maybe throw that up way at the top here. So what we're going to do is we're going to take the mass of hexane, 1.550 grams, and we're going to multiply by moles over grams. And the hexane is C6H14. So 6 times 12.01 plus 14 times 1.008 gives us 86.172. The grams cancel out. And so we can find the number of moles of hexane that were in this particular experiment. So that is 0.01798. This should have 4 significant figures, and I'll throw the 7 in there for good measure. And that is moles. We had this many moles of hexane. It generated this quantity of heat. So if we want to know how many kilojoules for 1 mole, we take this amount of kilojoules and divide by the number of moles. So we take 70.2498 kilojoules divided by 0.017987 moles. Yeah, I really need to get out my real calculator. 70.2498 divided by 0.017987. And how many significant figures should I report? 3. So the calculator is showing me 3905.6 other stuff. I want to keep 3. I'm rounding off to the tens place. That means I should put this in scientific notation before I round it off so I don't do something stupid. Times 10 to the 1, 2, 3. Now I can round it here and get 3.91 times 10 to the third kilojoules per mole.
Is it negative?
Yeah, it is negative. And this is where we really have to be able to think about what the negative means, because sometimes you have to you have to keep the negative sign, and sometimes it seems to not matter. Make my box bigger. Point. So yes, there's a negative there. What they're asking for is the delta E for the reaction. That should have a sign, either positive or negative. Sometimes they'll say, calculate the amount of heat lost in kilojoules per mole. Sometimes the sign is implied by the words. And so with mastering chemistry, you need to be a little careful with that. Any questions?